Welcome to this explainer on performance considerations and readiness for migration, brought to you by Forge College. So in our last explainer, we tackled testing and mocking for our ported contracts, right? We basically made sure the code actually functions as intended. But today, we're kind of switching gears. We're putting on our hard hats and stepping into the role of the home inspector. You see, our ported EVM code might pass all the tests with flying colors, but now we've got to closely inspect those blueprints to ensure it runs efficiently on Solana's unique architecture. We're moving from just making it work to making it work beautifully, and more importantly, efficiently under the hood.
Okay, let's dive right into this. Here's our 6-part inspection report for today. First, testing to performance. Second, spotting the compute hotspots. Third, optimizing reads and writes. Fourth, your optimization workflow. Fifth, the readiness checklist. And finally, number 6, final review and next steps. This is exactly what we need to go over to get fully prepared for that final capstone migration.
Section 1. From testing to performance, shifting the mindset. Up until now, our primary focus has really been on functional correctness. Does the contract compile? Do the unit tests pass? Do our mocks handle external state correctly? But when you're moving from the Ethereum virtual machine to the Solana virtual machine, a passing test suite is literally only half the battle. Now we have to start evaluating performance trade-offs.
And that leads us to the absolute golden question. Does it just work, or does it work efficiently? Are you ready to stop looking for simple syntax bugs and start hunting down the absolute compute hogs hiding deep within your smart contracts? Because on Solana, inefficient code doesn't just look a bit messy, it eats up compute units and can cause your transactions to just fail outright. There's no way we want that.
Let's take a second to really contrast these two paradigms. On the EVM side of things, your main enemy is storage space, right? Reading and writing to state is where you pay the absolute heaviest gas penalties. But jump over to Solana, and the main constraints flip. It's all about buffer traversals and compute units. Bringing naive EVM habits over to Solana is, well, it's totally counterproductive. It's basically like unpacking your entire 50-pound suitcase every single time you need to find one pair of socks, and then repacking the whole shebang right after. Sure, it works, but man, the overhead is completely exhausting.
Moving right along to Section 2, spotting the compute hotspots, finding the friction in the gears. So how do we actually stop unpacking that giant suitcase unnecessarily? Well, we need to find the friction points in our machine. And when porting from EVM, there are generally 3 prime suspects that cause the most compute inflation.
Let's look at the schematics for these culprits. First up, we've got repeated deserialization. This is our classic suitcase problem. Every single time you deserialize, you traverse the entire buffer, and that eats up massive amounts of compute units. The fix? Pretty simple, actually. Just deserialize once, keep it in memory, do your thing, and then serialize exactly once at the very end. Next on the list, multiple small CPIs, or cross-program invocations. Each CPI has invocation overhead. It's kind of like calling an expensive contractor out to your house 5 separate times to fix 5 different tiles. Just batch them into a single job, right? Lastly, large account allocations. On Solana, you literally pay rent for space. So if you reserve a massive empty warehouse for just a couple of boxes, you're wasting valuable resources. You really need to compact your data layouts and offload any infrequently used fields.
All right, on to Section 3, optimizing reads and writes, oiling the gears. Now that we've identified the friction, let's look at how we actually apply the oil. We're going to transition over to some code-level mitigations for our absolute biggest culprit, that naive EVM approach to deserializing accounts multiple times in a single flow.
Here is the optimized path, broken down step by step. Step 1. Perform a single mutable borrow of your account data. Just get it once. Step 2. Do all of your math, your balance updates, your timestamp changes, do it all right there in memory. And then Step 3. Perform a single final serialize to write that newly updated state back to the buffer. By avoiding those repeated buffer traversals, this one simple structural change can literally save you tens to hundreds of compute units per instruction. Honestly, it's a real game changer. It is the lowest effort, highest impact optimization you can possibly make.
Which brings us to Section 4, your performance optimization workflow, the repeatable process. Of course, knowing the tricks is one thing, but applying them methodically, that's another beast entirely. We need a systematic approach. You can't just guess what's slowing down your program. You need a repeatable process to turn those test failures and profiler outputs into prioritized engineering tasks.
Now, what's really cool about this workflow is that it forms an endless loop of improvement. Step 1. Collect your baseline metrics. Ask yourself, how many CUs are we burning right now? Step 2. Trace and annotate your logs to find exactly which lines of code spike the usage. Step 3. Isolate those top hotspots. Step 4. Propose your targeted mitigations, like consolidating those writes we talked about, or batching your CPIs. Step 5 is absolutely critical. Validate. Did your fix actually save CUs? You have to measure it. And finally, Step 6. Document it for your reviewers. Measurement is the absolute necessity here, folks. You've got to prove your optimization with hard data, not just intuition.
Section 5. The Migration Readiness Checklist, the Inspector's Report. This brings us to the really practical application. All of this testing, tracing, and fixing culminates in building the actual artifact needed to get the green light for your capstone migration. We call this the Migration Readiness Checklist. Let's look at a concrete example using an ERC20-like token port.
Let's review these metrics real quick. For the Mint flow, we proved optimization by dropping compute units from 45,000 all the way down to 36,000. How? Simply by removing a legacy bookkeeping CPI. Pretty awesome, right? For the permit flow, the signature parsing was just way too heavy, so we made a smart design trade-off. High-value verifications stay on-chain, but low-value approvals get moved off to the client side. And for batch transfers, we aggregated changes in memory but restricted the batch size to 20 recipients just to avoid hitting any transaction size limits. Plus, all these changes come with clearly documented rationales and the required security signoffs attached. Hard numbers, clear decisions, that's the name of the game.
So, the crucial point here is this exact definition. Your readiness checklist isn't just some quick to-do list scribbled on a napkin. It is a fully documented artifact. It's literally the ultimate proof of your operational readiness. It tells your product owners and your security reviewers, hey, I measured the costs, I optimized the hotspots, I accepted the necessary trade-offs, and here is the mathematical proof. It builds so much trust.
And that brings us to Section 6, Final Review and Next Steps, closing the migration loop. We are almost at the finish line, guys. It's time to finalize our inspection report, sign off on the schematics, and prepare to hand over these highly optimized blueprints to the rest of the team.
This statement brilliantly illustrates the absolute gold standard for migration acceptance criteria. When you can hand a document to your reviewer that essentially says this exact quote, where X and Y are your hard, validated limits, you remove all the ambiguity. The product owner knows exactly what they're getting. The security team knows exactly what compromises were made. It's clean, it's totally professional, and it proves you are absolutely ready for the mainnet.
All of these artifacts we've discussed today feed directly into your next big step, the capstone kickoff, where you'll map out your scope, risks, and the final migration plan. By doing all this hard work right now, you ensure that kickoff goes smoothly without any last-minute compute unit surprises. So, as you prepare for your own capstone, I want you to ask yourself a final question. Is your ported code just checking the boxes to pass tests, or is it truly engineered to scale gracefully on a high-speed network like Solana? I highly encourage you to take these concepts and really practice them. For more resources, deeper dives, and the ton of excellent Web3 content, make sure to visit forge.college. Thank you so much for joining me on this explainer by Forge College, and happy optimizing.